Hello, everyone, and welcome to today's webinar, addressing unique catalyst deactivation challenges for converting biomass-derived feedstocks. Our speaker today is Huamin Wang of Pacific Northwest National Labs. Before we get started, I'll go over a few items so you know how to participate. You're listening in using your computer speaker system by default. If you would prefer to join over the phone, please select telephone in the audio pane of your control panel, and the dial-in information will be displayed. We are taking questions via the chat function on the bottom of your control panel. Questions will be answered at the end of the webinar. We will be recording today's webinar. You will receive a follow-up email within a few weeks with a link to view the recording. Thank you so much for attending, and now I'll turn it over to Huamin.
Hey, Hannah, can you hear me? Hello, Hannah.
Yes, go ahead and start your presentation now. Thank you.
Can you hear me now?
Yes, we can hear you now.
Sorry, I had some little problem. Okay, great, thank you. Hello, everyone, and welcome to today's ChemCatBio webinar. My name is Huamin Wang, and I'm a senior research engineer here at the Pacific Northwest National Laboratory. And today I'm going to share with you how we're addressing those unique biomass conversion challenges, including catalyst deactivation challenges for biomass conversion in our ChemCatBio consortium. So specifically in today's presentation, I will show you that ChemCatBio is tackling overarching catalysis challenges for biomass conversion, especially including improving catalyst lifetime is one of its critical goals. And this is specifically important for biomass conversion technology because biomass-derived feedstock bring a lot of new challenges for catalyst lifetime or catalyst stability. And I will specifically present some examples of our efforts on understanding and mitigating catalytic deactivation within ChemCatBio and also other related projects, especially on zeolite and oxide catalysts for aqueous phase conversion reactions, and also specifically on catalysis, especially metal catalysts for pyrolysis, vapor, and oil upgrading. And ChemCatBio, or Chemical Catalysis for Bioenergy, is a national lab lead R&D consortium. Our mission is to accelerate the development of the catalysts and related technology for the commercialization of biomass-derived fuels and chemicals. So we are leveraging expertise and capability across 7 national labs for catalysis study, including advanced synthesis and characterization, and multi-scale, catalyst evaluation, and assisted with modeling and simulation efforts by computational. So as you see that ChemCatBio is working on catalysis because catalysis plays a central role in biomass conversion, and catalysis challenges are one of the biggest barriers in biomass conversion. When you look at across the variety of different conversion pathways for biomass conversion, including biochemical approach or thermochemical approach or hybrid approach, there is always a catalysis step, including heterogeneous catalysis. And within ChemCatBio, we're specifically working on a lot of important catalytic processes within biomass conversion, including catalytic upgrade and biological intermediates, and catalytic fast pyrolysis, syngas upgrading, and catalytic upgrading aqueous phase or gas phase waste streams, and catalytic hydrotreating. And what makes catalyst R&D in biomass conversion more challenging is that biomass presents lots of unique properties, as shown in here that it has lots of oxygen there, so and also have lots of diverse chemical functionalities. Therefore, we have to consider competing reactions and make our catalyst more selective to certain desired reactions. And more important, as showing highlight over here, is that lots of those kind of biomass-derived feedstock had water contact and the impurity there that causing lots of problems for catalyst deactivation and catalyst lifetime. So we all know that catalyst lifetime is important as its activity and selectivity. For industrial relevant process, we have to demonstrate catalyst stability to meet the production performance goal or requirement for this process. However, in some early stage R&D, the catalysis or catalyst stability is normally receiving less attention compared to its activity and selectivity. Within our ChemCatBio consortium, we believe that understanding of the catalyst deactivation and developing strategies to extend the catalyst lifetime are critical to the success of the process development for biomass conversion. And it's especially important for biomass-derived feedstock because it brings new challenges to this issue. Compared to the fossil feedstock, most of the biomass-derived feedstock are complex, highly fractionalized, and unstable. I'm showing here examples that bio oil, which is a phospholysis product from biomass, contains lots of reactive species. It will go through some condensation reaction or polymerization reaction to form high molecular weight stuff and to eventually plug your catalyst pore and eventually plug your reactor. At the same time, biomass-derived feedstock could contain contaminants, either from biomass itself or from the process unit. But those contaminants can be in organic form like sulfur or nitrogen-containing species, or be inorganic like lots of minerals or as shown over here. A third problem is challenging for biomass-derived feedstock that it normally contains lots of water or corrosive species like carbonic acid. Basically, this requires our catalyst to be working under aqueous phase or corrosive conditions. So here I will give in the next few slides, I will provide a summary of how these unique properties of biomass-derived feedstock could cause catalyst deactivation on different types of catalysts we normally use for biomass conversion, and how the mitigation approach can be used to address those issues. Those are information based on reported result in literature or based on our research at ChemCatBio. So we can group those kind of a challenging property of biomass-derived feedstock into heavy species, reactive species, contaminants, and water corrosiveness. And at different type of catalyst, it causes different type of deactivation. For instance, like catalyst falling, poisoning, or degradation. The mitigation approach can normally include catalyst regeneration or catalyst improvement to be more resistant to this deactivation mechanism or process improvement, including removing those troublemaking species from our feedstock. Let's first look at a reactive, heavy species and a reactive species issue. For heavy species, is normally from the conversion of the biomass, which is a high molecular weight polymer, into our intermediate product, and it normally has residue high molecular weight species. Those high molecular weight species can also be formed by reactive species in the biomass-derived feedstock, especially from those aldehyde ketones that by condensation reaction or polymerization reaction to form those heavy species. So those heavy species can easily, cause catalytic deactivation by falling, and this falling is somehow more some chemical or just a physical problem. Therefore, it kind of working on pretty much all the catalysts we're using over, this biomass conversion. And the mitigation approach can be regeneration to burn off those coke, or by process improvement to remove those heavy species or reactive species in our feedstock. There are some good examples like listing here that, for instance, bio-oil hydrogenation can be falling by heavy species is really a problem and can be generated by cleaning method. Or zeolite catalyst using for catalytic phospholysis can be formed by those condensation products and coke, and can be regenerated by oxidation. Also, other example, and one unique one is like HMF to for dicarbonic acid approach that normally the catalyst will be forming by the form FDCA will cause catalytic deactivation, and this can be partly addressed by using special solvents for this process. Therefore, you can remove FDCA as soon as it was formed. The second big problem for this biomass conversion regarding catalytic deactivation is contaminants. And we know that, as I just listed, there's lots of sulfur nitrogen-containing species in certain biomass feedstock and also inorganics from biomass or process unit. Depending on the type of catalyst, like sulfur can cause the poisoning of metal catalyst, inorganic can cause poisoning of our acid-base catalyst, and nitrogen can cause poisoning of our bronze acid catalyst. So those poisoning will cause, apparently will cause catalytic deactivation, and mitigation approach can be regeneration or process improvement. Some example including like ruthenium catalyst for different approach, different application, and can be poisoned by sulfur, and this can be either regenerated by regeneration to remove sulfur from poisoned catalyst or by removing sulfur from our feedstock. I'll give you more specific example on this sulfur problem. So last one is water and corrosiveness. I just mentioned that there's lots of water in our is involved in a biomass conversion process, and in this case, it really is going to impact a lot of metal oxide-based catalyst or zeolite type catalysts, causing catalyst centering or degradation or phase transition. And the way to normally to do is to mitigate those deactivations is either by catalytic improvement to make catalyst more robust towards those water issues, or by process improvement, and especially to remove water and get a relatively clean, pure organic feedstock for this chemistry. Example in literature including aqueous hydrogenation reaction use nickel catalyst, and in aqueous feed it can form nickel hydroxide and hydroxide, and this can be partially mitigated by catalyst surface hydrophobization to limit the water near catalyst surface. Or for the carbon catalyst and carbon leaching problem, and therefore you can stabilize this carbon species on catalyst surface by atomic laser deposition. So hopefully I showed you that overall big picture that how those unique properties of the biomass derived feedstock could impact the catalytic deactivation, and what's the kind of general approach to mitigate that. So in following slides or 20 minutes, I'll give you some specific examples for those aspects, and those are examples either from our related biomass conversion projects, and also primarily from our ChemCatBio consortium. So our start with those, I just mentioned the aqueous phase conversion or water corrosiveness issues. I'll show you two examples on catalyst stability improvement for aqueous phase reaction, especially in hot liquid water. I'll give you first example on stability of zeolite improvement for aqueous phase dehydration reaction, and this is based on research at Pyongyang funded by our internal LDRD. I'll give you a second example on enhancing hydrothermal stability of zirconia catalyst for catalyzation reaction of acetic acid in aqueous phase. And this is work is funded by our ChemCatBio, and is as you can see that is all those work is reported in literature, and you can see more information from the paper cited over here. So let's start with zeolite catalyst. So why we are working on zeolite for this liquid phase reaction. So as shown in this figure that dehydration reaction, as shown here, alcohol dehydration is one of the most important and straightforward method to remove oxygen from our biomass intermediates. However, most of this dehydration reaction can be catalyzed by a bronze acid like a proton or zeolite. Problem for this reaction is that this reaction was very fast on gas phase over zeolite catalyst, but as soon as you put this zeolite catalyst in a liquid water, and therefore you want to convert those alcohols in liquid water without separation. So now the problem is that the water will interact with those protons and form a hydrated hydrogen ion, which will significantly lower the ability of those bronze acid site to do the dehydration catalysis. So by using zeolite, I'm showing this figure that zeolite cannot only enhance or enrich those organics in the pore, therefore to increase the concentration of the alcohol in the pore, but also can provide a confinement impact to get a much faster turnover rate of those bronze acid site after the water hydration. So as shown in this picture that by using MFI zeolite, we can see 100 times faster turnover rates over alcohol dehydration compared to free liquid acids. This makes the zeolite to be a very attractive catalyst for aqueous phase dehydration reaction. Of course, the immediate question is that how stable is this zeolite for this application? And yes, there is a problem that zeolite is not stable in hot liquid water. And shown in this table, and just simply process or treat the zeolite, beta zeolite, in liquid water at 106 degrees C, we do see a significant drop at surface area and pore volume. This is because the hydrolysis of zeolite framework and the partial dissolution of the crystal in liquid water is causing deconstruction of those zeolite structure. So with the further extensive study showed that this kind of deconstruction is because of a cylinder defect site over those zeolite. As showing in this table that after we treat the zeolite with silylation, as shown in the left-hand side, after silylation, and MR showed that we actually removed those cylinder defect site from zeolite. By doing that, and we actually lose some surface area and pore volume, but we largely maintain its stability. And as showing, last line, and after water treatment of this silylation zeolite, and we do see the surface area and the pore volume is largely maintained, really showing that it is true that the cylinder defect site is the cause of structural instability of zeolite in hot liquid water. And by silylation treatment, we can improve its stability. However, by just controlling the silylation or cylinder defect site is not sufficient. The concentration of intraporous water also directly related to the role of rate of hydrolysis of zeolite framework. As shown in left-hand side, that we are changing the bronze acid density by changing the silicon lumen ratio of zeolite. You can see that we are increasing the water uptake with increase in bronze acid density. This is both true for a defect beta zeolite or low defect beta zeolite, really showing that because of the existence of bronze acid site, we do have a lot of water in the pore. This water will cause a problem, of the stability of zeolite. And in the left-hand side, in the right-hand side, you can see that this is really true that only at a lower bronze acid density zeolite, we can have a much increased lifetime. And the silylation method or the lower defect density is only important at low concentration of the bronze acid site or low concentration water inside. This really tells us that we have to control the water contact within the zeolite pore to further mitigate this deactivation problem. And another approach is that to do external hydrophobization. And in this figure, we show that by doing external hydrophobization of zeolite, we can have a much improved lifetime activity. This is, we believe this is because of the limitation of diffusion of liquid water into the pore, and therefore to further decrease the concentration of water inside the zeolite and further enhance its stability. So with this research, we hope that we have now a toolbox for zeolite stability enhancement in hot liquid water. This toolbox including started with a lower defect density, especially the silica defect density, by either synthesizing a fluoride media to get a more crystalline structure and therefore less defect size, or by some post-synthesis treatment like silylation. Or at the same time, we need to lower the water contact in the zeolite pore by tuning silica lumen ratio and generally lower the density of the bronze acid density. At the same time, by some external surface modification like external hydrophobicity. That's showing here that we do have a lot of this kind of existing knowledge on catalyst stability mitigation from related project at different national levels, and ChemCatBio will definitely leverage of this knowledge for developing stable catalysts, especially for this zeolite system, and we're going to leverage whatever we learned over here for upgrading biologically derived intermediate in liquid phase. So now I'm going to a more complicated system, and this is another system and working on enhance the stability of zirconia catalyst for direct catalytic upgrading aqueous phase carbonic acid. This is a relatively more complex system compared to the alcohol in water, because this is a system from the hydrothermal liquefaction. And for woody biomass after the hydrothermal liquefaction, or HTL, a lot of carbon will end up into aqueous fraction. And in this aqueous fraction, the majority of carbon is in carbonic acid form. And there's also other species, and especially sugar-derived species. And one of the strategies to use this carbonic acid carbon in HTL aqueous phase is to do ketonization reaction, showing here, to convert those carbonic acid into ketones. And ketones from ketone will be more straightforward for steam reforming to produce hydrogen, or by hydrogenation and dehydration, we can get olefin from that. So for this ketonization reaction, the zirconia catalyst is showing very good performance, and especially in gas phase. However, as soon as you put the zirconia in this liquid phase, and especially in very diluted carbonic acid, like 5% or below in water, as shown in left-hand side, we do see a fast deactivation of zirconia for this application. And for the characterization of this zirconia catalyst, I show in the middle of XRD, and we do see that bottom is a fresh zirconia. As soon as you treat the zirconia in water or in carbonic acid, and we do see a phase transition, from the tetragonal zirconia to monoclinic. And the team actually spent a lot of effort to really mitigate this catalyst deactivation by using lanthanum doping to really not only enhance the activity of this catalyst, and showing in left-hand side, and also prevent those phase transition, and showing in the right-hand side that after using lanthanum doping, and this catalyst is maintain its tetragonal zirconia phase in water or in carbonic acid condition. By that, this catalyst was demonstrated more than 1,000 hours lifetime for this application, and this is reported in this paper I cited over here. I think I showed you that we do have a lot of nice study to understand how can we, mitigate this deactivation bring by condensed water reaction. And now I'm going to a much more complex system here, like fast pyrolysis. So fast pyrolysis is a process that I can treat the biomass directly in a high temperature, and followed by a fast quenching, then you can get a liquid. And here, the bio-oil itself, I will talk more about that. Bio-oil itself too has a significant problem regarding its upgrading to produce fuel products. In order to enhance the quality of the bio-oil, there's two approaches to do that. One is that you can produce bio-oil and then to do a bio-oil stabilization to increase its quality for hydrotreating, or you can use catalyst during fast pyrolysis, which we call catalytic fast pyrolysis, to directly react with the fast pyrolysis vapor to produce a stable or high quality COP bio-oil. Today, I'm going to show you that how we are going to mitigate, catalyst deactivation during those fast pyrolysis bio stabilization step. This is a work done by PM and Oak Ridge and under ChemCatBio for fast pyrolysis bio quality improvement. And also, I'll give you another example that is an ongoing effort at ChemCatBio on catalytic fast pyrolysis, that how are we understanding the deactivation mechanism of the catalyst used for this catalytic fast pyrolysis. This is a collaboration effort between PM, NREL, and Oak Ridge, and also multiple projects within ChemCatBio. So I just mentioned that for after fast pyrolysis, we have the bio-oil, and this bio-oil really is a low quality. The quality is not only because it has a lot of oxygen, a lot of water, and the low heating value, but the major problem is that the bio-oil is unstable, and it will causing, it will undergo some condensation reaction to form the high molecular species, and encapsulate your hydrotreating catalyst, and even practically react if you directly feed this bio in the hydrotreater. And therefore, I just mentioned the bio-oil quality improvement can enable those direct hydrotreating, and those improvement currently including bio-oil stabilization by a low temperature hydrogenation reaction, or pyrolysis vapor catalytic upgrading, we call it catalytic fast process. Both the process are using kind of reduced metal catalysts and with hydrogen and doing those lots of catalytic reaction, including hydrogenation and HDO. Let's start with a fast process by oil stabilization by hydrogenation. So as I just mentioned, a raw bio-oil, if you put into a reactor, a hydrotreater around 400 degrees C, pretty much the reactor will plug within 1 day. And our previous work showed that if we can stabilize bio-oil by doing low temperature hydrogenation, and the first generation of low temperature stabilization by using sulfide catalyst and can partially stabilize bio-oil, however, is that not sufficiently enough? And normally we will see a reactor plugging around 100 hours. This is really showing, asking us to really kind of conduct deep stabilization. And the so-called deep stabilization, and I'm showing you here, is that is really doing a low temperature hydrogenation. And what we learned that if we do deep stabilization, that bio-oil will be able to process in a hydrotreater more than 6 days without plugging. What is really happening during the deep stabilization? So before that, let's look at what in the bio-oil and what is causing problem. In bio-oil, you will have a lot of sugar-derived species, which is low glucosan or a lot of aldehyde ketones. And at the same time, we have phenolics, or those phenolic oligomers from the lignin. And of course, we have a lot of carbonic acids. So basically, you see those species over there, that they can undergo a lot of condensation reaction to either from humans or even from those highly molecular species or resins. And those products, those reactions will occur as low as 80 degrees C. And that means that in order to compete this reaction, we have to do stabilization reaction at low temperature. And the approach we are doing that to do low temperature hydrogenation, and we saturate those aldehyde ketones and phenolic into alcohols. And we have to do this reaction again at a very low temperature. And what we found that a reduced ruthenium catalyst can do this job very well. It can do hydrogenation at low temperature as low as 120 degrees C. Therefore, it can well compete with those condensation reaction and stabilize bio-oil. However, in order to do that, we have to use a reduced metal, and sulfur poisoning is always a problem for this reduced metal catalyst. As shown here, that with time on stream, we use hydrogen consumption as an indicator for the catalyst activity, and we're showing that the catalyst activity is dropping with time on stream. We find that this deactivation rate directly linked to the sulfur content in our bio-oil. We're comparing two bio-oils. They're exact same bio-oil. We are managing to vary the sulfur content, and we see that at lower sulfur content, we can have a slower deactivation rate. This is further confirmed the post-catalyst characterization. We have much more data than that, but I just highlight the most important one here, that really showing that at a bio-oil with lower sulfur content, we have much lower sulfur on a spent catalyst, really showing that sulfur poison is a major deactivation mode for this catalyst. However, at the same time, we do see a co-formation over those spent catalysts, as showing here that it's always 5 to 6% of carbon on a spent catalyst, really showing that for polymerization, and we call it the coke here, but it's not exactly the same coke that refinery talking about. That those polymer formation or coke formation also contribute to the catalyst deactivation as a secondary deactivation mode, over sulfur, especially over sulfur poison catalyst. So in order to manage this sulfur problem, and what we do is that we either lower sulfur content in bio-oil to enable improve the catalyst stability, and showing here that for bio-oil, if we use a lower cost base metal as a guard bed, we can kind of treat this bio-oil to lower this sulfur content below 10 ppm. By doing that, as shown here, the carbonyl contact with time on stream, and we do see a much improved carbonyl reduction, and we get much less carbonyl in our product, which is our desired goal. And we do see a much stable catalyst over here. And most recently, together with feedstock conversion interface consortium, we also found that we can control sulfur contact in bio-oil by controlling the moisture ash contact in your biomass feedstock. I'm showing you this figure that normally if we have a lower ash or lower moisture contact, we can get a bio-oil with much lower sulfur content, as shown here, 19 ppm sulfur, and it's definitely showing a much improved catalyst stability for this hydrogenation over ruthenium catalyst. A second strategy is that we can do catalyst generation. So we are since we are running our reaction at a relatively low temperature, which makes lots of sulfur poisoning is more like chemabsorption of those sulfur-containing organo species rather than high temperature H2S and surface sulfiding. So with this one, we can use some solvent method to kind of clean or extract those sulfur species and the coke species over our catalyst surface. So we developed a two-stage like cleaning approach to really, first stage to remove those polymer from spent catalyst, and second stage to remove sulfur species from this catalyst, and then we do re-reduction and put back for the bio-oil stabilization. So basically, by doing that, I'm showing this figure that we will see after the first cycle, we will lose like 20% of catalyst lifetime. This is just because there's certain sulfur is strongly bonded on our surface that cannot be removed. However, after the first cycle, in second and third or fourth cycle, we do see that it kind of reached the pseudo steady state that this catalyst is maintain its activity after this each regeneration. So basically that we can design a multiple reactor system to do this bio hydrogenation, and for certain reactors in series and certain reactors in regeneration. Together with a lower sulfur content, if we control our biomass feedstock very well, so we can achieve more than a year lifetime of this receiving catalyst for bio hydrogenation. However, we have to do some further on development for this process, because this process so far is demonstrated on over oak, like a hardwood bio-oil, but we still have some questions need to be answered to use this the process for other bio-oils, especially softwood bio-oils. So let's now focus on the CLP. CLP, as just mentioned, is a user catalyst during fast processes, especially here that at ChemCatBio, we are more focusing on this ex situ fixed bed CLP. Basically, after the fast process reactor, the process vapor will be cleaned by a hot gas filter, and then the vapor will go through a fixed bed reactor to do various reaction to upgrade this vapor into a more, improved bio-oil for hydrotreating. So this enables more diverse catalyst chemistry and require, but however, you can imagine as a fixed bed, it requires much long catalyst lifetime. And therefore, understanding the deactivation mechanism of this catalyst is critical. And showing here that we are using, NREL team developed this very nice, platinum or titanium catalyst, and leveraging its biofunctionalities, including a metallic functionality here provided by platinum, and also acid-base functionality provided by TiO2 support. However, this catalyst also have deactivation problems, and it will deactivate during those single cycle runs, primarily by coke formation. After oxidation regeneration, catalyst activity will be largely recovered, but however, we do concern is long-term stability, and understanding this mechanism will be critical. So we received CLP catalyst after 200 hours run, and we probe its change compared to a fresh catalyst by combining detailed characterization with kinetic study, and showing here that we specifically focusing on the HDO activity over a platinum active site, and also dehydration or aldehyde condensation reaction over a TiO2 active site. What we learned is that first, that active site activity is largely maintained, and we were not finding sulfur on this spec candidate, which is really a good news that the majority of active sites in this catalyst is maintained, and sulfur poisoning are the most challenging issue is not here. However, we do see that accumulation of the potassium in this case, and potassium is from the biomass feedstock, and is keep accumulating over this spent catalyst. And also, we do see that the platinum particle size is changing upon the different treatment and different regeneration during this process. And lastly, that we did a kinetic study and the acid site density and titration. We find that most of the acid site was largely maintained, but there's some loss just because of a surface area loss. With this preliminary characterization of spent catalyst, we found that changing the platinum particle size and accumulation of potassium could potentially impact this catalyst lifetime in longer term. And we specifically focus on potassium issues, that potassium accumulation is not only for this specific system, is also widely observed in situ and ex situ CLP and hydropolysis. Specifically for this process, we found that potassium accumulation is more occurring on the leading edge of the catalyst bed, as shown in this figure. That at top of the catalyst bed, we see more potassium deposition. However, we believe that with time upstream that this potassium deposition will start to impact our catalyst in the middle or the bottom. So now really questions that how is potassium distributed at atomic scale, and what's the consequence in catalysis. So we have some preliminary data with ACRC and showing that potassium deposition on leading edge is true by XPS analysis. And further, TM images suggest that this potassium is uniformly distributed on catalyst surface. That's really important information, that because if this potassium will form a large clusters or crystals somewhere, maybe less a problem. But if it's uniformly distributed on catalyst surface and may interact with active site, that causes a problem. Therefore, we have a catalyst deactivation mitigation project within ChemCatBio, and specifically focus on this potassium accumulation on catalyst surface and understand its consequence regarding its catalyst activity. So in this case, and we conducted controlled deposition of potassium with different loading over a plan or titanium catalyst, and conducted extensive characterization and evaluation. And first, then we found that by doing this, we actually can duplicate what we observed on a real spent catalyst, and we get a uniform distributed potassium over those catalyst surface. And the characterization really shows that by those potassium deposition, we are not influencing surface area or metal site density or metal surface area of this catalyst, but more acid-base site density, as shown here. And we further conducted extensive kinetic study over this spent catalyst and potassium deposited catalyst. And here we are showing that for dehydration reaction, what we learned is that by loading potassium on this surface, and we do see an increase of the dehydration rate. At the same time, we are not only seeing the decrease of dehydration rate, but also we see an increase apparent activation energy for this reaction. This really tells us that the potassium is not only killing the active site, but also killing a different active site or modifying the active site from a strong active site to a weak active site. However, for HDO reaction, we find that it will require almost 200 ppm of potassium to start to see a negative impact of potassium deposition for HDO reaction around a platinum active site. At the same time, it looks like activation energy for this reaction at different potassium loading is pretty consistent, right, showing that this is more like deposition or poisoning of active site rather than modifying active site. Based on this information, we propose that for potassium impact on this catalyst system, and basically for clean surface, you do have a metal active site and loose active site, or TiO2. And at low potassium loading, that potassium looks like more deposit or remote to the loose acid site, and only impacts the loose acidity and therefore dehydration or acid-base catalysis reactions. At the higher potassium loading, the potassium start to interact with the interfacial sites, and therefore start to interact. You start to inhibit the HDO reaction, as shown in the bottom. So basically, we know that interaction of potassium with active site really depends on the potassium loading and leads to different catalytic consequences. So with this information, it will enable us to predict the catalytic performance at different time stream, and therefore different potassium deposition, and also help us to understand that what's the catalytic degradation or catalytic generation will like, and how much potassium we should remove from this system, therefore to recover the activity. Okay, hopefully today I showed you that within ChemCatBio, we are tackling overarching catalysis challenges for biomass corrosion, and we are specifically including this improving catalytic lifetime as one of our most important goals. This is important just because biomass-derived feedstocks bring new challenge to catalytic lifetime and catalytic stability issue. I hope that I showed you those examples on ChemCatBio's efforts on understanding and mitigating catalytic degradation, especially on how we are modifying zeolite and oxide catalysts to enable improved stability for active phase reaction. How are we managing sulfur, or how are we developing catalyst generation protocol to extend the ruthenium catalyst lifetime for biostabilization? And how are we conducting, foundational understanding of deactivation mechanism of those palladium anti-titanium catalyst for catalytic phospholysis, which could lead to process and catalytic improvement. So this is really a team effort at multiple national labs and multiple projects within ChemCatBio, and the people participated in this research are listed here, and I really appreciate it. And we especially thank the support from Bioenergy Technology Office for those projects, and also for the whole ChemCatBio. And with that, I would like to thank you for your attention, and I would like to take any questions if we have enough time. Thank you.
Thank you, Huamin. We have a couple of questions. The first one is about the slides. Getting a copy of the slides. If you look on the control panel, there's a gray bar that says handouts, and if you click on that, you can actually download the slides right now, but we will also be sending them out after the presentation with a link to the video recording. We have another question for Huamin. What is the fouling of catalyst by heavy species?
Oh, okay, thank you for the question. So fouling the catalyst by heavy species is like, for instance, like phospholysis, that not all the primary structure of the biomass was decomposed during phospholysis. You do have those oligomers of sugar or oligomers or lignin existing by oil. Those really high molecular weight species do have diffusion problem or do have reactivity problems. Therefore, it cannot be converted in our especially low temperature hydrogenation reactor. It will just physically deposit on your catalyst surface that cause a problem. This is also true for other processes. For instance, the active phase products from hydrothermal liquefaction and unconverted sugar oligomers will do the same thing. We basically just a high molecular weight species deposit on your catalyst surface to encapsulate the catalyst, therefore to prevent diffusion of reactants into the catalyst pore and even further, plug your reactor. And this is what I'm referring for in the high molecular species in the biomass-derived feedstock for catalyst fouling.
Thank you. Are there any other questions from the audience? You can type it in the chat panel on the right-hand side in the control panel. There's a gray bar that says chat. I'm going to leave it open for just one more minute to see if there are any other questions. All right, here's another one. During ex situ CFP, were the flue gases from the char combustor passed over the catalyst bed? Have you tried bypassing the catalyst bed when combusting the char? And did you still observe K poisoning?
Yeah, my understanding is that for this process, currently we are using a hot gas filter before this fixed bed reactor. Therefore, the char from the phospholysis vapor will be largely removed from this by those hot gas filter, and therefore definitely there will be coke formation on this catalyst system, and we are conducting regeneration of this catalyst by burning off the coke by oxidation approach, definitely, and we do see the potassium accumulation on this case. So that means there's potassium still, although char is removed, but still there's potassium in vapor and depositing on the catalyst surface.
All right, the next question. Any research on catalyst for xylose conversion to xylitol via hydrogenation?
My understanding, at least within ChemCatBio, there's no such research, but I will definitely double check with that.
Okay. I'll leave it open for just any other questions that the audience might have. We can also answer questions offline if you'd like to add them in. Oh, here's another one. Have you tried surface hydrophobization supported metal catalysts?
Yes, actually, this is one of our idea of dealing with, those bio-oil hydrogenation or similar catalyst systems that by doing surface hydrophiltration, you can, limit the water concentration near the catalyst surface, or therefore near our metal sites or near our acid-base sites, therefore can somehow protect this catalyst from, any problem induced by water. That's definitely a good approach for that. Thank you.
Question is, follow up on that is what support?
You mean this question? Yeah,
yes.
it will be more like transition metal oxide or zeolite support, those oxides, definitely. But of course, if you can do modification, carbon is also important, but somehow carbon has some limitation because oxidation regeneration may not be able to apply on carbon support catalyst.
Okay, thank you. All right, we have another question. Process control is going to be key here, as in feedstock quality and product formation. The feedstock quality is going to vary as much as any current production line that exists in this area. Understanding that will be key in its control. We'll be in touch.
Thank you for the question. Exactly. I think as I just want to present briefly that we do have a feedstock conversion interface consortium is specifically asking this type of question, that what's the change in the feedstock on the process is going to impact the downstream quality of downstream quality of a product and also a downstream process. And the catalyst lifetime or catalyst stability is one factor we're considering there. As I just present that, for instance, ash contact or moisture contact in feedstock could impact sulfur content in our product, and therefore impact our bio-oil hydrogenating or hydrogenation catalyst lifetime. So this is one of very important area that I think National Lab are dealing on the battle, and we do have those consortium like feedstock conversion interface is dealing with these questions. Yeah.
Thank you. The next question is, what are your regeneration methods?
Can you specify which process?
It was not specific about, bio-oil.
Okay, so in general, if you are talking about bio-oil stabilization, our generation is solvent cleaning. As I mentioned that since the reaction has a relatively low temperature, so lots of those sulfur species are, like chemisorption of those organosulfur or sulfur, carbon and sulfur compounds over catalyst surface. It's not a H2S poison the catalyst. Therefore, we can use some solvent to really weak the metal sulfur bonding and then remove this organosulfur to regenerate. In general, for this low temperature hydrogenation of bio-oil, we're using a solvent washing method to regenerate catalyst. For the high temperature one, as just mentioned, that we use oxidation method to reduce to remove those coke. And for potassium, we're still working on that, but in literature you can see for zeolite catalyst, mild acid washing can somehow remove those potassium and therefore regenerate this catalyst.
All right, thank you. Wait just one more minute. Any other questions from the audience? All right, well, thank you so much. Thank you, everyone. Thank you, Hua Min. Thank you for attending today's webinar. You will receive a follow-up email within the next few weeks with a link to view a recording of today's webinar. You can share that. Thank you for joining us today, and have a great rest of your day.